Hey folks, how's it going? It's Mr. Murray coming to you with a video introducing you to this brand new concept that we're talking about today called rational functions. This year, it's actually kind of represents the beginning of the end in a sense, right? It's the last unit we're going to talk about this school year at least. And it's really a great unit because it's a great way to end the year. It takes a lot of the skills that we've talked about and it ties them together really, really nicely. And so I'm really excited to be ending on this note. Okay, so what is a rational function? Well, a rational function is a function of the form f of x equals p of x over q of x, where p of x and q of x are polynomials. You may have been wondering in this slide, well, what is with all these numbers? Well, you might have remembered that these numbers are all called rational numbers because they're ratios of integers, right? 1 over 2, 2 over 3, negative 2 over 3, and so on. Just like you can have ratios of integers, you can have ratios of polynomials. And when you define a polynomial by taking a function by taking a polynomial and dividing by another, that gives you what's called a rational function, because instead of a ratio of numbers, you have a ratio of polynomials. Now, the most basic rational function, sometimes called the parent function, with a variable expression in the denominator, is f of x equals 1 over x. And so I thought I'd start by talking and trying to go through the idea of, well, what does f of x equals 1 over x even look like, right? This is a brand new function with x playing a different role than we've seen in some of the other functions we've studied so far over the past couple of years. So the first thing I notice is that, well, this is just taking a number and dividing by another number. So as I always do when I want to make a graph, and I really don't have any other knowledge, right? At this point, there's no tricks, there's no ability to just use any tools and just magically create a graph, right? By waving our magical wand. We actually need to plot this thing, and there's no information we have. So in the end, it comes down to the idea that a table is always a strategy that works. So let's think about some numbers we could plug in. Well, if I plug in 1 for x, I'm going to be doing 1 divided by, and then you're plugging in down here. So 1, you get 1 divided by 1, which is 1. If I plug in 2, I get 1 divided by 2, which is 1/2. If I get 3, that would be, you can see it would be a third. If I get 4, it would be a quarter, and so on and so on. And you can imagine if I did a 10, it would be 1 out of 10. Okay. What about the negative direction? Well, if I plug in -1, I get 1 over -1, and that is -1. And you notice if I plug in 2, well, it's not that much different with -2 as +2. It's just that now, because it's a positive over a negative, you're going to get a negative result. The same thing is true with -3, right? It's not very much different than +3. It's just that now you have a negative number, right? -4 gives you -1/4, right? And -10 would give you -1/10, all right? But now I bet you're wondering, Mr. Murray, what about 0? Right? You plugged in positives, you plugged in negatives. What about 0? And there's a reason I didn't plug that in. And the reason is because we know that 1 out of 0 is undefined, right? In other words, 0 is not a number that can be plugged in to this function, because when you do that, you're going to be dividing by 0, and we know that that is not something that we can do. So this is an interesting function here, because what this is getting at is that we are actually going to have a whole class of functions, the rational functions, where there's going to be one or more x values that we're not going to be able to plug in. And that's true across every kind of rational function. And that's unique, right? Because we're always used to saying the domain is -infinity to infinity. But that's not true anymore, right? Because now we know we can plug in anything, but we can't plug in 0. So That's going to be interesting. So 0 is not actually a value. What about some fractions? What if I plugged in a half? Well, what's 1 divided by a half? Well, that would be 2, because it would be 1 times 2. If you plug in a third, well, what's 1 over a third? That's going to be 3. Okay, similarly, if we plugged in negative a half, we would get negative 2, because it's the same process, right? And as with negative 3, but a negative number. So by using what we have here, let's try to see if we can generate out a graph. Oh, very interesting. So we have a half going to 2. We've got a third going to 3. So this is really, really interesting. Now, this is a kind of function that we studied last year, it looks like, right? Called the exponential function. And the exponential function, you might remember, had a horizontal asymptote because there was a y value you could never have. This one's a little bit different. Let's take a look. So I'm going to get a similar thing here, right? So except here, it's going to come down along this side. And now it's going to shoot way down like this. So this is the graph of the parent function, f of x equals 1 over x. Some things that are worth noting, right? Again, you can see a couple interesting things here. So you can see that there are a couple magical lines, and I'm going to go ahead and just quickly point them out. So first, we have this magical line right here. This green line that I've just put on the screen is a special line. Let me just make that a little bit thicker so everyone can see it. So I've got this line here, but then in green, okay? But then I've also got this line here, and I'm going to put this line in red. Okay, so let's make it actually purple. So let's take a look. I've got a green and a purple line. You're going to notice that for both of these lines, the graph is coming really, really close to it, but never actually touching the line. The purple line is what we call a horizontal asymptote. And this came up last year in Course 1 Honors when we were discussing exponential functions. They would always have an output that you could never quite get to, and that would be represented by a horizontal asymptote. Introducing in this, we talk about the green line, which is a vertical asymptote. And what it represents is the fact that we can get really, really close to 0 for our x values, and we'll still have an output. But once you plug in 0, it's suddenly undefined, and you no longer get that output. Okay? Notice how as we approach 0 on both sides, on one hand, as we come from the right, if we're in the positive x values, it's shooting up to infinity, and on the other end, it's shooting down to negative infinity. This idea of up and going up and pointing down, right? This is what you're going to see happening around a vertical asymptote. You're going to see it pointing up, or you're going to see it pointing down as you approach that line. Whether they point in the same direction or other or opposite directions, which one points up and which points down, that does depend on a few factors. And so we'll discuss some of those in this video today. All right, now that we have our parent function, let's talk about some analysis. So we've already talked about the domain. And the domain, we now know, is everything that is not 0. So there's a few ways to write this. The first way you could write this is with inequality notation. So x is either greater than 0 or x is less than 0. So x is less than 0 or x is greater than 0. Okay? That is the domain. So we're saying everything but not 0. It's either less than 0 or it's more than 0. It's not equal to 0. The second method is called set notation. So all the x values where, that means where or such that, x is not equal to 0. You just use those squigglies. Third way is with interval notation. So negative infinity to 0, u 0 to infinity. So I'm just saying everything but 0. So these are 3 different ways to say that x is any number you want but it's not 0. Okay, for the range, it's going to be a similar thing. So here, we can see that y is everything we want, but it can never be 0. It can be positives, it can be negatives, but it can't be 0. So we can say that in 3 ways. Either y is greater than 0 or y is less than 0. We can say it as all of the y values where y is not equal to 0. Or we could say it as negative infinity to 0 union 0 to infinity. In the homeworks and HRW assignments, you may be asked to state it in a number of different ways, right? This is inequality, this is set, and this is interval. All right, vertical asymptote. In the parent function here, the vertical asymptote, okay, is going to be given by the line x is equal to 0. It's vertical, so I should see x equals. It's 0 because that's the up and down line, right? X equals 0. Okay, we talked about this as well this year a little bit earlier on when we talked about writing axes of symmetry for parabolas that point left or point right. Horizontal asymptote, because it's horizontal, I want to see y equals, in this case y equals 0. Where is it increasing? Okay, so as I go from left to right, where are the values going up? And the answer is nowhere. Why? So think about it. From left to right, as I go from left to right, they're going down, 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 right? They're starting close to 0, but they're getting more and more and more and more negative. So they're decreasing. Then all of a sudden, after 0, right, I'm still decreasing. So it's decreasing everywhere. So it's decreasing from negative infinity to 0. It is going down. And then from 0 to infinity. So similar, we start to see a pattern. It's either increasing everywhere or decreasing everywhere. Whether that will always be true remains to be seen. But the idea of how you evaluate increasing and decreasing hasn't changed from any of the other functions we've seen before. All right, even, odd, and neither. So what I want to know is, here's just a quick recap. A function is considered to be even if f of x equals f of negative x. That is to say, if you plug in a negative number, it's the same as if you plugging in the positive number. So for example, x squared, 2 and negative 2, 3 and negative 3, 5 and negative 5, 15 and negative 15, whatever number and its opposite will always be the same when you square them, right? Like 2 squared is 4, negative 2 squared is 4, 15 squared is 225, negative 15 squared is 225. So that's an even function. So is 1 over x the same thing as 1 over negative x? No, of course it's not. And we know that, and we talked about that earlier, right? The fact that 1/2 and negative 1/2, you can see here, an example right here, right? Another example. You clearly, when you make x negative, you do not get the same output. So it is not even. Could it be odd? So odd is when negative f of x is equal to f of negative x. So it's almost like you can remove, like factor out the negative and you get the same thing. So is 1 over negative x equal to negative 1 over x? Yeah. Yep. They're exactly the same thing because it doesn't matter where you stick the negative. This is an odd function. It is an odd function. So if you plug in negative 2, it's equal to negative what you'd get if you plug in positive 2, right? When you plug in positive 2, you get a half. When you plug in negative 2, you get negative a half. When you plug in 3, you get a third. When you plug in negative 3, you get negative a third. Okay, so that is an odd function. Finally, end behavior. So as x goes to infinity, what's happening? As x gets to infinity, f of x is getting closer and closer, but not equal to 0. And as x goes to negative infinity, f of x is also getting closer and closer to 0. Now, it is true that 1 is 0 on the negative side and 1 is 0 on the positive side. And we are going to have to think about it. So what I'm saying is, yes, it is approaching 0, but the values on the left are going to be negative as they approach 0, right? So negative a tenth, negative 11th, negative 100th, negative 1,000th, negative 1/1,000,000, etc., etc., etc. But on the right-hand side, they're going to be positive a tenth, positive 100th, positive 1,000th, and so on. Okay? So what that means is this is something we're going to have to think about, because we're going to want to start to think about how we can use these patterns when we have to deal with more complicated types of rational functions. So hopefully this made sense to you. I really encourage you to rewind and review anything I've done here, including the analysis and the graphing. And then in a moment, I'm going to start talking about about the more general types of rational functions. Okay, folks, so these are the general forms that you're going to see when you look at rational functions. So you can see that we have an a, an h, and a k in this first one, just like we've seen in all the kinds of functions we've seen throughout high school, right? Quadratics has a vertex form with a, h, and k. What do we have? Absolute value has a form with AH and K. Linear equations, M and B, but it also has an AH and K with the point slope form, right? So the H and the K come up so often. And then right this year we talked about the square root function with an H and a K and the cube root function with an H and a K. So every type of function that we've learned about seems like it's got some form of HK. And if I had access to my HK board that I usually have in class, this would be up there too, right? So essentially, this is what we're going to see the functions be presented in. And what these represent, just as with any of the other forms, is transformations of the graph of 1 over x into another function. So we're going to be looking at in this video a variety of strategies in terms of how we graph it. We can talk about doing it in terms of transformations. We're going to talk about it in terms of simplifying, and we'll see polynomial division come back. So there's lots of things to think about here. Okay, so if I'm going to start to analyze this, I want to start by looking at some patterns. So here we have a table, and on the left, what we have is the parent function. Well, on the right, we have the transformed function. Okay, and so some common things we're going to want to look at are the horizontal asymptote, the vertical asymptote, and a couple of reference points. Why? So one of the most important things we're going to need to do here is we're going to need to identify the asymptotes, because what you've hopefully seen if you look at the parent function is once we define and we get those two asymptotes laid out, the function is essentially just going to dance around those two asymptotes. So that is going to be the secret here, and the good news is the HK finds us those values we're looking for. So the vertical asymptote, just by a reminder, is a vertical line that the graph gets close to but never touches, and it represents an input that does not have a defined output. For example, in the parent function, when I plugged in 0, you don't get a defined output because you can't divide by 0. If you were to try to put it into your calculator, right, you would get an error. So that could be another way to talk about it in terms of a calculator. A vertical asymptote represents an input that when you plug it into your calculator, you get an error because it can't give you the output. On the other hand, a horizontal asymptote is similar, except it's a horizontal line that the graph gets close to and doesn't touch, and it represents an output that there's no possible input you'll ever get to match up with it, right? So we talked about here with 1 over x, we could never ever get it to be equal to 0, because no matter how big, or rather how positive or negative you made x, you could never get the fraction to equal 0. And that indicated a horizontal asymptote of y equals 0. Finally, sometimes we use what we call reference points. And so reference points are convenient points that are easily calculable and can be used to determine how a function is being transformed. What I'm getting at is, it's a couple of easy points that help us figure some stuff out. Because let's think about it here, right? So going back to our parent function, if I'm able to find the two asymptotes, I know how the function dances or where it dances around. Is it above or is it below? Where is it going here? But here's the thing. If I didn't give you these two pieces that you see graphed of 1 over x, and I just give you the asymptote, well, how do I know that this piece isn't above, right? How do I know this piece isn't above it, right? If I hadn't made a table and I had only used the rules of the asymptotes, there's no definitive way to know that. So reference points help give us a sense of what's going on. We chose -1 and 1 because those were easy numbers to plug in. You can see in the example here that they've essentially chosen -b plus h. Why do they do that? Here's why. Because when you plug in -b plus h, watch what happens. They're just trying to make it as easy as they can. And the idea is you essentially want to make a fraction that comes out to a nice whole number. So what happens here, if I was to plug in -b plus h, right, you'd get 1 over b, -b plus h, right? When you plug in -b plus h, but then you also have the fact, and I'm sure I'm going to have to erase and rewrite, you also have the fact, so that's your x value, right? And then that, you're subtracting h. I'm looking down in this denominator here, but when you do that, the h's will cancel, and you get 1 over b times -b, but that is equal to -1. And then it boils down to simply 1 over -1. So you take a very complicated denominator and you make that denominator equal to 1, because anything divided by 1 is itself, right? So just like how I say, oh, make the parentheses equal to 0, maybe we have a little strategy here. Make the denominator equal to 1 somehow, and we'll have a really easy point to calculate, because it's easy to divide by 1. If you divide a number by 1, you get the number you started with, right? Okay, so what do we do with this? Well, let's take a look. So I'm going to graph the function. I was given the function 3 times 1 over x minus 1 in parentheses plus 2. So when I'm given this, the first thing that I notice is that I have a vertical stretch by a factor of 3. So if I go back and look at this, this is an indicator. This is going to be my vertical stretch and shrink, just like it is for quadratics, just like it is for exponentials, just like it is for absolute value, for linear, for all of them. That's the same role it plays. This is going to be, as you might expect, this is going to be my left or right translation, and the k is going to be my up or down translation. Okay, so coming back here, we can see a vertical stretch by a factor of 3, followed by a translation 1 to the right and 2 up. Okay, the left and right kind of works a little bit quirky, just like it more or less always does. All right, so let's try to actually and analyze this. And before we do this, note that the translation of 1 unit to the right affects only the x coordinates, while the vertical stretch by a factor of 3 and the translation by 2 units up only affect the y coordinates. So what they do here is they actually use point notation, where we take the -1, and because we are moving it to the right, we're adding 1 to it, and they put that with 0, -1. But I'm going to say is this. Forget about this for a second. There's another way that you could approach solving a problem like this. If I want to do this and I want to get a couple good reference points, think about for a second. Forget these points real quick. All right, look at the denominator. It's a pain in the butt. If I could make this denominator 1, it would be really easy, because 1 over 1 is 1. So how do I make the denominator 1? Well, what number, when you take away 1, do you get 1? It's 2. So if I plug in 2, the denominator becomes 1. And so what happens from there? Well, I get 1 over 1 is 1. 3 times 1 is 3. And 3 plus 2 is 5. So it's a very similar strategy. You plug in to intentionally get an easy number in the denominator. And then if you want to know what y is from there, you just finish doing it out. So what's another good number to get in the denominator? Well, what about negative 1? Because 1 over negative 1 is negative 1. And that's a real easy number to work with. Well, how would I get what number minus 1 would be negative 1? And that would be 0. So 0 minus 1 is negative 1. 1 over negative 1 is negative 1. 3 times negative 1 is negative 3. Negative 3 plus 2 is negative 1. Okay, so now you can see that essentially they did get the same answers as me. I just think the way it's done here is a little bit more confusing. Just look, think about this. You need to get x's that will give you easy y's. Make the denominator 1 and you will get an easy y, right? Think about it like that. Just make the denominator as easy as you can. You make it 0, right? You get your horizontal asymptote, right? Your vertical asymptote rather, right? We can see that 1 makes it 0. We can also see that we can pull our vertical asymptote. Anyway, let's talk domain and range. Interesting thing we see here, and that is that if you take a look at the domain and range, well, the domain and range are based around the vertical and horizontal asymptote. Since once we know that the vertical asymptote is 1 in this case, because 1 makes the function undefined, we then take that and we say the domain is everything but 1. Once we know that the horizontal asymptote is 2, that tells us the y's are everything but 2. And so that's how we essentially write it. Please just make note of the 3 ways in which we can do this. I'm not going to go into a super big detail here because we will see examples of it coming right up. All right, so here's a graph, and this transforms the graph of f of x that in these ways, okay? So you've got a horizontal compression by a factor of 1 over 2. And that's because, remember, if you're like, wait, 1 over 2, remember that 2 is equal to 1 over b. So what would b have to be for this to be true? Well, switch places, b equals 1/2. So when you just have to be careful there, okay? And if you're like, wait, what? Go back to this form. It looks just like this one on the bottom. So when you see it like this, this represents a horizontal stretch. So going back to our example, we also see a translation of 3 units left, be careful with the sign, and 1 unit down. Again, it's like opposite and like the same, kind of like how it's always been. So remember, I always say think about what makes equal to 0, and I think you'll be in pretty good shape. So, okay, let's take a look at this graph right here. Forget about the transformation stuff right now, and let's see if we can find the asymptote. So look, we cannot plug in x is equal to -3, because if we do, we get -3 plus 3 is 0. 2 times 0 is 0. You can't divide by 0, so it's undefined. That's good. What's the horizontal asymptote? For the horizontal asymptote, you look to our k value here, and that is -1. And if you think about it, the k value has a similar role in many other functions. It's actually also the horizontal asymptote for a exponential function as well. All right, reference points. Look, this is a bunch. Forget this. Forget this. It's stressful. Forget it. Let's look at the function. I want to make this denominator a really, really nice and easy denominator, right? I want this to be equal to 1 or -1. So how could I make it equal to 1? Because if I can do that, right, I get 1 over 1, which is 1, and 1 minus 1 is 0, right? If I can just make this 1. So how could I do that? Well, I could divide this by 2. And then actually the parentheses would be gone. And now I'm going to subtract the 3. And I get x is equal to minus 2.5. So if I was to plug in minus 2.5, I would get minus 2.5 plus 3 is positive 1/2. Right? Negative 2.5 plus 3 is positive 1/2. 2 times 1/2 is 1. 1 divided by 1 is 1. 1 minus 1 is 0. So negative 2.5 comma 0. This stuff gets really, really confusing. Okay, so instead, I'm going to think about making the denominator a nice number. So first I make it 1. Now I'm going to make it -1. Because if I can make it -1, it'll also be nice easy, right? It'll be 1 divided by -1. And that's a nice easy thing to calculate, right? So the goal is get 2 nice points, make it really easy to figure out. So now what I'm going to do is I'm going to come in and I'm going to do the same thing, right? I start by dividing by 2. Nothing changes about that. And now I'm going to subtract 3, and I get negative 3.5. So negative 3.5. And then when I plug in negative 3.5, I get negative 3.5 plus 3, which is -1/2. 2 times -1/2 is -1. 1 divided by -1 is -1. -1 minus 1 is -2. Okay? Notice how these have a difference of 2, just like how these have a difference of 2, and that's what you would expect because there's no not necessarily like any kind of vertical stretching. So we can see some things are like preserved there. And you can actually see that if we did the function notation. All right. So this is actually what the graph would look like. You can see that we have our, well, first, this is the graph of this one. We're going to have to make the graph of this one. So in any case, we know this. So this is the graph of 1 over x. We need to do this one. And so what we have is we have a vertical asymptote at -3. We have a horizontal asymptote at -1. So our graph is going to dance around this right here. Now at -2.5, I'm at 0. All right. And at -3.5, I'm at -2. So what that tells me is my graph is going to look like this because a point exists, right? So basically, the fact that there's a point here means that the graph exists in this part of this, right? It's almost like this getting cut into quarters, right? So because there's actually a point here with an x and a y, we know that some of the graph is up in that corner here. And similarly, because we know that this point here exists, we know that it's on the graph in this part of it. Now, was this a great graph? No. I was inhibited somewhat by the use of my pen, but the goal right now is to just kind of draw a rough graph, okay? So for example, if I'd gotten 3.5 positive 2, then that would have told me that the graph was up here. So again, we're using the asymptotes to give us this kind of like boundary, saying where does the graph live? The graph has to be bounded by these two lines, right? It's got to be closed, told exactly where to go by them, like directed. By finding reference points, we can then figure out how the original function is being transformed and where the new function is. So the fact that, again, negative 2.50 is a point on the graph tells us that some of the graph is up here, and the fact that we know that negative 3.5, negative 2 is a point on the graph tells us that the other piece is down there. Now let's talk about domain and range. So the domain is everything but negative 3. Okay, so it can't be negative 3. So it's either all the numbers less than negative 3 or greater than negative 3. It's all the values of x that are not equal to negative 3, or it's this interval notation right here. Okay? And then the range of g of x. Well, this tells us that it's all the y's that are not negative 1 based on that horizontal asymptote. So either y is less than negative 1 or greater than negative 1. Y is all the values that are not equal to negative 1. And as interval notation, negative infinity to negative 1, union negative 1 to infinity. You can write the plus infinity or not. That's not a big deal. Okay, so things to think about. We got to think about some patterns that we're noticing and how those patterns are kind of manifesting themselves in the points that we're finding. But if we can kind of put together our vertical asymptote and our horizontal asymptote, we're going to know essentially, have a sense of where this graph is, right? We'll have our four little corners, four little pieces, and then by using our reference points, we're going to figure out which two pieces we're going to find the graph in, okay? So we have the graph negative 0.5 times 1 over x plus 1 to the minus 3. Okay, so I have f of x equals 1 over x already graphed. You might not be able to tell because of how the graph has been cut up, but notice how this graph is not like a negative 1 to 10. Like, it's not the same as I usually make my graph, right? So what you're going to do is on this coordinate plane, and I encourage you to make a table if needed, you're going to try to identify the transformations from 1 over x to this function. If you need to graph it first, that's fine. What you're going to do is you need to also make a graph of this function as this same coordinate plane. We need to think about our asymptotes in helping us do that. And then we need to find the domain and range using inequalities, set notation, and interval notation. There will be another problem if you're kind of confused about what I'm looking for you to do, but please at this time pause your video, try the best you can to create the graph, describe the transformations, and do the domain and range, and then when you're ready, unpause and you can see what I got. Okay, so here we go. I'm going to start by trying to make sense of what we got going on here. So the first thing I notice is I'm going to do my horizontal asymptote and my vertical asymptote first. So the first thing I notice is that the vertical asymptote is going to be x is equal to negative 1. And I know that because when I plug in negative 1, I get 0 in that denominator, and my x is on, and that's going to make my g of x undefined, right? So that is going to mean that's a pretty good sign that I know it's going to be dancing around that negative 1. Okay. Now, next, horizontal asymptote is going to be y equals negative 3. I'm just going to pull it right off the end. Okay? And essentially, remember, what's happening with 1 over x plus 1 is either x is getting really big and 1 over x plus 1 is going towards 0, because you think about 1 over a big number, or x plus 1 is getting really small and 1 over x plus 1 is getting very large or far from 0, right? And so negative 3 is essentially what's remaining. When you're very close to 0, negative 3 basically has all the value. when the y's are far from 0, then negative 3 basically doesn't do much of anything at all, right? If negative 0.5 times 1 over x plus 1 was 100 million, well, what would negative 3 be compared to that? Think about it like that. So here's our asymptotes. So it's going to be dancing around here. Now, I need my reference points. I'm going to completely ignore the negative 1, 1. I don't even know what that means. I want to make this denominator 1. What's going to make this denominator 1? Let's make x equal to 0. If I plug in 0, what's 0 plus 1? It's 1. So I get 1 over 1. 1/2 times 1 is negative 1/2. Negative 1/2 minus 3 is negative 3.5. So I have 0, negative 3.5. Okay, now I want to make it negative 1. What would make the denominator negative 1? X is negative 2. So if x is negative 2, I get 1 over negative 1 minus 3. So this is negative 1, and negative 1 times negative 0.5 is positive 0.5. So I end up with negative 2.5. So negative 2, negative 2.5. So let's see what it looks like. First, I get 0, 1, 2, 3.5. And then I'm also going to get, on the other side, it looks like negative 2, negative 2.5. Interesting. Okay. So what I should see happening is I should see something kind of like this. And we can see if we can describe what happens. Just going to sharpen that up a little bit. And you could try to graph this on your graphing calculator with a little bit more accuracy. So basically, there's 3 transformations that are going on right now. Or at least 3. What we have is, we actually have 4. First, we have a reflection over the line y is equal to 0. Now, if you think about it, right, this one's going down, this one's like this, and if you think about it, instead of going down, you can imagine taking this piece going down and flipping it over that x-axis, y equals 0. And you can imagine doing something similar here. So you have the reflection over y equals 0 of both of those parts. You then also have a vertical shrink, or compression, or dilation. You have a translation to the, now think about this is positive, so you're going to the left by 1, and then you have a translation, I'll maybe just do an L, translation down by 3. Okay, the 1 and the 3, we should be able to get those pretty straightforward just by looking at the asymptotes. The reflection, you should be able to see that in terms of looking at where it is. So here it's in the upper left and the bottom right, whereas maybe like before it was located, see, in the other 2 corners, and we could see that our thing was positive in there. Hey folks, so I thought I'd take a moment to show you how we would do this in our graphing calculator. I was very fortunate to regain access to mine. So what we would do is we would open up our graphing calculator. I just had this from a previous video I was doing, so I'll clear those out. Now let's type it in. So negative 0.5, 1 plus 1 divided by, make another parenthesis because you don't want to be doing 1 over x. You want to be doing 1 over x plus 1. Close the first one, close the second one, minus 3. I also found this really cool setting. If you go to mode and you go down to this setting right here where you see full, and you go over and select graph table or GT on some of the older model calculators, when you do graph, it'll actually build it side by side with your table here. Okay, so that's mode, scroll down and look for graph table, rewind if needed, and you can see that our graph is matching the graph that I made. Again, my graph is not perfect. You can see that it's not exactly the same, but if you can give me a general sketch and describe the transformations, that's a really, really good start. Remember, you can also feel free at any time to do second, table, or you may have to actually, before doing that, reset full to full. And if you just want to see the table after that, you can go second table. But that's the whole thing. So again, mode, you go down midway to where you see full, horizontal, and graph table. And you select graph table. And then you hit graph. And you see them side by side. All right. Next thing we need to talk about is what happens when we are not actually given something in one of these forms. The answer is we turn it into something in one of these forms. So what we're going to do is we're essentially going to use our long division to do that. So when given a rational function of the form g of x equals mx plus n over px plus q, where m and p aren't 0, meaning they're two linear functions, you can use long division, so that is you do the numerator divided by the denominator, to write the function in one of the two forms, which will then allow us to graph it. Let's take a look. Okay, so here we have 3x minus 4 over x plus 1. Remember, this is one method we can use. We could also use the method of synthetic division. So I put a 1 here because this is a minus 1. And I put a 3 and a negative 4. Remember, this is the bus method. I bring down the 3. I multiply the 3 by the 1. I add down. And I get negative 1 as my remainder and 3 as my quotient. Just like we get in the long division. It's your choice how you want to do it. Other method you could use, remember we talked about, is the box method. It's very more difficult to use this one, but you essentially have x and minus 1, and here you put in your 3x. This needs to be 3, so you get 3x, 3 times x. This gives me negative 3. And since this is actually done, but since I need to have negative 4 in total, I need to have a remainder of negative 1, because negative 3 plus negative 1 equals negative 4. So remember, that is the one where it's tougher to understand the remainder. So you can divide however you want, but we do need to recall our polynomial long division skills. And I know it's understandable, but I know we haven't done that in a while. Okay, so here the quotient is 3 and the remainder is negative 1, no matter how you do it. So we rewrite it using this rule that we did for long division. And we had done this one kind of in the past. So you take the quotient, the answer, and you do 3 plus the remainder over the thing you were dividing by. Okay? And so what we've done is, because these are equal to each other, this is the answer to this division problem. Instead of graphing this initial function, I'm going to graph this one instead. And I can see it's got a vertical asymptote at 1, a horizontal asymptote at 3, and then we can plug in our reference points. I would plug in 0, so I could get negative 1 and 4, or rather, and 2, So I could get positive 1. They did transformation notation. You do your pick. And then you can see they did the domain and the range here as well. Let's try it one ourselves. So I've got 4x minus 7 over negative 2x plus 4. Let's see what we can do. So I'm going to use long division. I'm going to use, unfortunately, because of the negative 2x, I cannot use practically the bus method. So I'm going to use the box method. And I only need one column in my box. Okay, so this is 4x. And this is negative 2x. So I need this to be equal to negative 4. So this needs to be negative 2 because negative 2x times negative 2 is 4x. Okay, but I know since I'm dividing by negative 2x plus 4 that if this is negative 2, this is negative 8. So if this was negative 2x, I'd have negative, but I want negative 7, so I need r being equal to negative 1. So I get a remainder of negative 1. Here's the other way to do it. Remember, we could also do it with polynomial long division. So I do the leading term, so I ask myself, what do I need to multiply negative 2x by to get positive 4x? The answer is 2. And then I distribute 2 times negative 2x, or 2 times, this needs to be negative 2, sorry. So negative 2 times negative 2x is 4x. Negative 2 times 4 is minus 8. And then these cancel, and negative 7 minus negative 8 is positive 1. So this should actually be a positive 1. So easy to get those things mixed up. See, this one had to be a negative 1 because we need to drop it down to 4. This one needs to be a positive 1 because we need to put it up to 7. Okay, so that's another way to see it, but in any case, we get a quotient of negative 2 and a remainder of 1. So we write it like this. We put our remainder there because that's how we write long division in that format. So we get 1, and then the other thing you could do is you could factor out the negative 2 because these both have a negative 2 in common. So we could rewrite it like that as well. And this negative 2 just comes from the idea that you can move it over to the other side. It doesn't matter what side that negative 2 is on. All right, so let's take a look. We have a vertical asymptote at x equals 2 and a horizontal asymptote at y equals negative 2. I'm going to kind of nix these right now because this is kind of making me stressed out. What makes my denominator 1? Well, what would make my denominator 1 would be if I had 2.5. Because if I had 2.5, 2.5 minus 2 is negative 2 times 0.5, or a half. And negative 2 times a half is negative 1. 1 over, so I get negative 3. So I get 2.5, negative 3. Okay, what about negative 1? Well, I would need this to be equal to, what if x was positive a half? Well, if x was positive a half, I would get 1. I need to be not positive a half, positive 1.5. 1.5 minus 2 is negative 1/2. Negative 2 times negative 1/2 is 1. And so what I get is 1 over 1 minus 2, which is 1 minus 2, which is negative 1. So I get 2.5 and 1/2. All right. So those are going to be my reference points here. So I've got 2.5, negative 3, and I've got 1.5, negative 1. And then I have my asymptotes at 2 and negative 2. All right. And so it looks like I'm going to get a graph that looks something like this, going up, and maybe something like this. All right, domain inequalities. So that means the domain would be everything but 2. So either less than 2 or more than 2, all the x's that are not 2, or negative infinity to 2 and 2 to infinity. And the range is going to be based on that horizontal asymptote. Y's less than negative 2 or more than negative 2. All the y's that are not negative 2 or negative infinity to negative 2 and negative 2 to infinity. All right, folks, so here's what I want you to do. I want you to use the box method, the bus method, or the long division method, whatever you want, to turn this thing here into one of these two forms. And then what I want you to do is I want you to graph it. Then I want you to state the domain and range using inequalities, set notation, and interval notation. So please pause the video, do that, and then when you're ready, unpause, and you can see what I got. Alright, folks, so I think I'm going to use the bus on this one. So I set up my negative 2 here. I put my 3 and my 8. I'm going to drop my 3 down. Multiply by the negative 2. That gives me negative 6. Add through. That gives me 2. So I have a quotient of 3 and a remainder of 2. So I'm going to write g of x is equal, ready for this? So here is my quotient plus 1. Well, actually, 2 is my remainder over x plus 2, because 3x plus 8 divided by x plus 2 is equal to 3 plus 2 over x plus 2, because the 2 represents the remainder. Now I'm going to rewrite it like this: 3 plus 2, and then in parentheses 1 over x plus 2. So now it looks like one of these forms right here. So first thing I'm noticing is my horizontal asymptote is x equals negative 2, and my vertical asymptote is y equals 3. Okay, I'm just going to draw these in with a line, since at this point I think a line's going to do a little bit of a better job than me. Okay. Now I need my reference points here. So I'm going to go ahead and I'm going to need to make the denominator. It would be really, really great if I could make this denominator 1. So I'm going to plug in negative 1. When I plug in negative 1, I get 3 plus 2 over 1 times 1 over 1, because negative 1 plus 2 is 1. So it's 3 plus 2, which is 5. So negative 1, 5. And then I have got, let's see. I want to make it negative 1, so I'm going to do negative 3. 3 plus 2 over 1, and this becomes negative 1, because negative 3 plus 2 is negative 1. So it becomes 3 minus 2, or 1. Negative 1, 2, 3, 1. So this one decelerating pretty rapidly. Okay, so the domain, 3 ways we could do the domain. X is less than negative 2 or greater than negative 2. The x's that are not equal to negative 2, or negative 2 to infinity, or negative infinity to negative 2. Okay, range, y is greater than 3 or y is less than 3. The y's that are not equal to 3 with squigglies, and negative infinity to 3 or 3 to infinity. Now, it doesn't matter what order you do the intervals. You should do the negative one first. I just happen to do those the other way around. But that's the general idea. So step 1, you're going to apply the, whatever division method to turn it into something that looks like it's in rational expression form. And then you're going to find the asymptotes and the reference points and go from there. Now, folks, we can model, but that's something we're going to be talking about in a later time. Okay, folks, that brings us to the end of our video. I hope you found this video to be helpful and kind of get you started with the ideas here. In the homework that I'm going to be assigning that follows from this video, I'm not going to be asking you to go super duper into detail in terms of your graphs. I am going to ask you to think about a few things. The transformations that are occurring, I am going to ask you to think about finding the domain and the range in the different forms. And then I'm going to be asking you to think about, overall, I'm going to be asking you to think about how a graph would be expected to look. All right, so folks, keep it up. Keep the questions coming. I'm looking forward to seeing everyone for Wednesday's Hangout. And don't forget, no matter how hard things get with these rationals, you can do it. All right, until next time, have a wonderful day.